Good afternoon, everyone. Thank you for coming along today, wherever you are in the world. We appreciate your time. So today we're going to follow up on our second of our presentations on production line testing, and we're going to talk about the Hipot test. For those of you that joined us on the previous webinar, which was all about creating safe environments, predominantly those safe environments are all around this particular test. This is deemed to be kind of the most risky on a production line. For those of you that did miss the first webinar that we did, if you are interested, please let us know and we can supply you a video link to review the webinar. So as we said, today's presentation is really going to be all about the Hipot test. It's probably the most important test that is performed on any production line and is critical for the safety of the product. So what are we going to look at today? Well, we'll be talking about the Hipot test itself. So what is it? We'll go through some of the definitions that you may hear as I go through the presentation, some of the more common terminology that you may hear if you talk about Hipot testing with anyone. We'll talk about why you should perform the test, what is actually tested during the Hipot. We'll discuss any kind of typical failures that you may see. We'll then move on to actually performing the test. So how is it performed? What connections do you need to make to the equipment you're performing the test to? We'll talk about the test parameters themselves, the voltages, the times, the pass limits that you should be looking to set within your production environment. We'll then discuss kind of AC or DC testing, whether the voltage should be at AC or DC. There's a couple of different kind of methodologies there and why you may choose to use one over the other. We'll talk about some of the standards and we'll give you some of the definitions within the standards. So we'll hopefully help you with potentially choosing the correct voltage, etc., for your particular standard. And then we'll have a couple of brief video demonstrations just to show you some of the tests in action and kind of solidify some of the comments that we make throughout the presentation today. So let's have a look at some of the common definitions you may hear me talk about today. We traditionally call it the Hipot test, but its official name is dielectric withstand testing. It's also commonly known as Hipot testing, as we refer to today, and that's basically taken from the term high potential, potential being another word for voltage. So effectively a Hipot test is a high voltage test. Commonly used across kind of the UK and Europe is a flash test. Now that derives its name from a particular condition known as a flashover, where current arcs from one point to another. So we typically call it a flash test here in the UK. Hipot testing is kind of more commonly used throughout the world, or in its kind of more basic form, you'll also hear it referred to as an electric strength test. And that ultimately is due to the test itself being a kind of measure of the strength of the electrical insulation, which leads us nicely on to insulation. We'll talk about that quite a bit today. What does insulation mean? Well, it's effectively a barrier between current carrying conductors. You may also hear of it called as a dielectric from the term dielectric withstand. So it's an insulation withstand test or a dielectric withstand test. The two kind of terminologies are interchangeable. Breakdown. Well, breakdown is effectively the point at which the insulation fails. It's the point at which a large amount of current is allowed to flow from one point to another. Effectively, it's the point at which the test fails. We also talk about leakage current. Now, that's the amount of current that flows away from the insulation into the return of the test equipment. So that's effectively the units of measure that we use. Our leakage current is any kind of current that's flowing away from the conductors we're testing onto the product chassis or earth cable and flowing back into the insulation. So we talk about leakage current as the leakage away from the insulation. And we also talk about trip current. So trip current is where we set a limit for the pass-fail condition. So if the leakage current hits a certain level, that level will initiate the failure condition, and that is what we know as the trip current of the test. So why should we perform the test? Well, ultimately, we want to ensure the product is safe to be used. That's our ultimate aim, is that we want to produce our products, ensuring that they're safe for our end users. So when they plug them into the mains and use them as as expected, that they're not going to be put into harm's way. But it also is a demonstration of compliance with any regional or international standards. So performing the test is a good way of ensuring that you're performing the test in the right way for your particular standard to demonstrate compliance through audit periods, etc. As a measure of quality control. So we know by doing the Hipot test that we may receive a certain level of leakage. Now we could use that leakage measurement as a method to ensure that we're always getting that same value, no matter when the product is built, no matter who is building it. If we get a set amount of leakage from known good products, if the product is built in the same way over and over and over again, then that leakage shouldn't change unless something deviates from the build process. And finally, we can use it as a measure of degradation. So if you are performing this test as part of a maintenance schedule rather than potentially a new build scenario, as the leakage current increases over time, we know that there's degradation going on. We can then do something about repairing the equipment before it becomes unsafe. So we perform the test for a number of reasons dependent upon your application. So a Hipot test is one of the core tests, as we spoke about earlier. There's generally 3 stages without a product or throughout a product's life cycle that we would perform a Hipot test. The first one is during the design phase, and it's part of what we call type testing. So this is almost a safe by design according to the standard. We've taken our product, we've built maybe a prototype of that product or the first production batch of that product. We need to make sure it's safe by design. So there's a number of things within the standard that we have to do to ensure compliance with the standard. One of those would be a type test. Now, the type test itself is typically a much longer test than, say, a routine or a maintenance type test. It's typically performed in the region of 1 to 2 minutes. So we're really stressing the product for a longer period of time, making sure it's nice and safe. Now, once we've had that test done, once we've compiled our report, we can then take the product into our factory acceptance or routine testing, or as we most commonly refer to it, a production line test. Now, that production line test is effectively a repeat of the type test, but at a much shorter period of time. Now, we know from doing the type test that it's safe by design, so therefore the procedures that we did to make the prototype should be repeated. The components will be the same as used at the type test period. So if everything is the same, the only thing that could potentially alter the safety of the product are things like the actual build process itself. So we're doing the test at the end of a production line to ensure that the build process or potentially any components that we've been supplied are still safe and still good to use. So we're not potentially worried about the fact that it was safe at design. We know that. What we're now concerned with is, has somebody or has the act of building it potentially made it weaker? Potentially somebody's overscrewed a screw and they've managed to pinch one of the live cables or something along those lines, or we've trapped the cable within 2 parts of the chassis, and then when we turn the power on, it potentially becomes live. And then the final time really where a Hipot test could be used is generally after service or repair or during maintenance. So this is just an ongoing, maybe a routine, regular test. Every time a product comes back for service, we're obviously taking the components apart, we're maybe opening the product up. So effectively, we may be potentially rebuilding the product after a repair. So we just want to make sure it's as safe as it ever was when it left the factory. So it can also be performed in that kind of area. Now, Hipot testing, there are 2 types of tests that can be performed on a product. There's what we call a dielectric breakdown test, and then there's what we call the more traditional dielectric withstand test. Now, the breakdown test itself is traditionally only performed at kind of R&D at the type test scenario. So the idea of a breakdown test is we just want to know exactly at what point the product fails. So effectively what we do, we take our product, we make the connections, and we start to increase the voltage. And we just continually increase the voltage until the point where the voltage is too much for the product and the insulating product components within the product fail, and we get a breakdown. So there's too much current flowing, the tester will fail. So as I said, it generally is only really performed as part of an R&D. We wouldn't do it on a production line purely because we're degrading the insulation. We're going to make the product weak. It's pretty much a destructive test. We certainly wouldn't want to do that test and then be shipping it off to end users. So the more common test that we tend to do is the withstand test. Now the withstand test is much more simple. We apply a known voltage, generally set by the standard or by methods we'll cover as we move through the presentation, for a set period of time. So we apply the voltage over a period of time, and providing nothing fails, then the product is deemed to be safe. We do that by monitoring the leakage current and making sure it's below our set failure point, i.e. our trip current. This is performed in both R&D, production, and the kind of maintenance areas. And it's typically non-destructive. As long as there's no failure condition, if the product passes, then the test itself is typically non-destructive. So the product can be safely used after this test. So what is tested during the installation? Well, very simply, if we are, any kind of manufacturer can incorporate two key safety features into any product to ensure it's safe. The first one being grounding. We fit a path to ensure that any fault currents will travel to ground, or we put insulation in the product, which acts as a barrier between any live parts and anything the user can touch, whether that's the chassis, the earthing, etc. Anything that provides a barrier between us and mains parts is insulation. And this is where the Hipot test comes into play. We're going to stress the insulation to make sure it's sound and doesn't provide a shock. So what is tested? Well, as we said, the idea of the test is to stress the insulation of the product under test above that of normal use. So we're typically doing it this voltage is much, much greater than the operating voltage of the product. It's used to detect any breakdown in the insulation properties of the item under test, i.e. does the product prevent shock hazards to a user by having sufficient levels of insulation? So we stress that insulation, make sure it doesn't break down, it holds that voltage in place without it becoming problematic. So failures, well, they could be indicative of any kind of problems with the design, the manufacturing processes, any incorrect or faulty components, or if you're doing kind of routine testing, any kind of wear and tear within the product itself. So the kind of typical failures that a Hipot test will pick up. Firstly, the most simple one are direct shorts. So any direct short between any of the line conductors, live or neutral, and the chassis or the earth cable if there's an earth cable in the product. Poor spacing. So if we have poor spacing between any kind of current carrying conductors, that can result in creepage or clearance distances being too small. We have too small a distance, and that in theory could present a flashover condition where the voltage and the current arcs from one point to the other point. Now that point that it could be arcing to through the insulation onto the chassis, which therefore provides a shock hazard. Any exposed wire strands or any crushed, pinched or split insulation will be highlighted by the Hipot test. It can also show any kind of supply issues. So you may be buying your cable in from a third party or any components, and you could have tiny, undetectable to the eye pinholes you can't necessarily see by looking. The Hipot test could pick that up. And kind of more on the maintenance side of things, if the product's being used in an environment where there are conductive materials present, they could build up over time and potentially cause a shock hazard. So the Hipot test is designed to find all of these fault conditions. It's truly a versatile test within our arsenal. So when we make the connection, how are we making this connection? Well, typically we're only making two connections. Although we may have multiple conductors, we're only making two connections. There's a positive end, or as it's commonly known, a hot or a high connection. And that connection is usually made to the main voltage carrying conductors. So your live, your neutral. We then have a negative, or again, it's commonly known as a cold or a low connection. And that's usually made to the chassis of the item under test. Now, where you do have multiple mains conductors, it's normal that we would strap those two conductors together and apply the voltage to the shorted conductors. Now, this isn't always necessary. You could perform the test multiple times. So you could do the test between the live and the chassis and the neutral and the chassis. But it's not prevalent that you do both. You can just short the two together. If there's any fault within either of the two conductors, that will still be highlighted. It will still flow to the chassis, and the test equipment will pick that fault condition up. So it depends on the connection method you have and how your tester works, but you could certainly make both connections or make manual shorting connections. So let's have a look at exactly how that potentially works. So here you'll see we have a Hipot tester and we have a diagram of our product under test. You can see we have a neutral conductor, we have a live conductor that flow through the load flows through, and then we have our chassis of our product. Well, the first thing that we would need to do is we would need to create a shorting condition between the neutral and the live conductors. So we're going to short those two together so we can send our high end or our test voltage up through the live and neutral, and we do that by applying a clip or a probe, etc., to those two shorted conductors. So now what we're doing is we're sending voltage in through the live and neutral. But as it stands, we've got no way of getting any kind of reference back into the instrument. So what we have to do is we have to supply a second connection, and that second connection would go onto the chassis of the product. And therefore, any current flow that flows away from the live or the neutral conductors and onto the chassis will then flow back into the instrument via the return of the test instrument. Now, for class 1 testing, that can be made via the earth terminal, or if your product is supplied on a plug, we can use the main conductors themselves within the plug as part of the test connections. So our live, neutral, and earth pins, we can use those as part of the test connection. Now, in this particular instance, we can use the earth connection as the return path for any leakage current. So as we just described, we have our live and neutral acting as the voltage in, and we have our chassis acting as the return via a crocodile clip. But we know with an earth connection, the earth connection is connected onto the chassis of the product. So it therefore goes in hand that if the current is flowing onto the chassis, then it will therefore be flowing back down through the earth cable. Now, what's really, really important is if you are going to use the earth cable as the return path, then we must ensure that the earth bond test has been completed prior to the Hipot test. And if we do have any earth straps that go off to multiple points within the product, we must make sure that the earth bond test is performed to each of those separate earth straps. So what we want to happen is that anywhere on the product, if there is any current flow, that any of those earth bond straps are doing their job, picking up that leakage current and flowing it all the way back, ultimately into the return terminal of the tester. So if you do have an earth product and you are doing Hipot testing, you can do the traditional method of putting a probe on, or we can use the earth clip, providing that we've performed earth bond tests prior to the Hipot test. So as you can see in this diagram, you can see now we have our ground conductor, and therefore again, if the current flow was to flow away from the live or neutral conductors onto the chassis, it will hit our ground conductor, it will flow back onto the return terminal of the tester, and any fault current, anything that's big enough to fail the test, will be picked up via that return. For a class 2 test, well, in this case, we don't have an earth connection. So we ultimately are relying on a return connection that we must manually apply to the product. So that may be a clip placed onto the chassis of the external product. It could be a probe if your particular testing equipment uses probes. We may need to apply a probe to return any fault current to earth. In certain circumstances, it may be prevalent or a requirement for you to use something like metal foil or conductive foam to aid in your test connections. We may have multiple points that we need to Hipot test with the class 2 product, particularly where you may have metal chassis separated by plastic onto a separate part of metal, etc., etc. So if there are multiple exposed conductive points, we need to make sure all of those exposed conductive points are Hipot tested. Now, the good thing about metal foil or conductive foam is we can effectively surround and wrap the entire product in one particular piece of metal or conductive casing. Therefore, any of those exposed conductors will be touching the foil or the foam, and therefore, if any of them have any leakage, then that will be picked up back at the return terminal. In that case, if you do use metal foil or conductive foam and you are completely encapsulating your product under test within the foil or foam, then typically you only need to do one test, that one test being onto the surface of the foil. If the current's flowing from anywhere, it will flow onto the foil and again back down through the return terminal of the product under test. So one of the common questions we get asked are, how are connections made when my product has a plug? Well, the easiest way to do it, and Seaward, like many manufacturers, have what we call outlet boxes. Now, these outlet boxes are quite simply a socket connection where you can take your plug it straight into the socket, and then the features are there to either via a hard shorting wire, the box will short out live and neutral together, or it may be done by relays. So the box itself, you plug the plug in, the box itself will take care of the shorting connections, and then it will also include a return path. Now, that return path is typically the earth pin, or there may be a separate connection for a probe if you need to use that. It does make for much more simple and fast and ultimately a safe connection by using one of these outlet boxes. If you are interested in any of these outlet boxes, please make contact. We have a range of these that could be used throughout the world. We have multiple kind of configurations of sockets. Okay, so let's move on now and talk about the actual test parameters themselves. The first thing we're going to talk about is the test voltage. Now, as good practice goes, I would always recommend that the first point of call for choosing a test voltage or any test parameter that we're going to talk about will be the manufacturing standard that you are claiming compliance with. They have within the standard guidance both for type testing environments and also for what they call routine testing environments, so the production line type testing. So always refer to the manufacturing standard where possible. We'll show you some examples of that a little later in the presentation. However, if you are unsure, if you're not sure what voltage, or if you're not sure what product standard you should be following, or if there is no product standard for your particular type of product that you're going to be testing, then there is a rule of thumb that you can follow. Now, that rule of thumb is quite simply your test voltage should be equal to voltage times 2 plus 1,000. The voltage that we're talking about here is the working voltage of the equipment under test. So as you can see in the example, we have a product that's rated for 240 volt operation. We would simply multiply 240 volts by 2 and then add 1,000 volts to that test voltage, giving us a test voltage of 1,480 volts AC. Now, there are many standards that you'll find that recommend a 1,500 volt test for a class 1 product. A good example of that would be EN 60958 for lighting, where the test voltage is 1,500 volts, which is near as damn exactly the same as 240 volts times 2 plus 1,000 volts. So that's where typically a 1,500 volt test is derived from. For class 2 products that are double or reinforced installation, it's normal then that the test voltage is performed at even higher voltages than a class 1 test. We call it double insulated because effectively it has 2 layers or more, or double layers of insulation or reinforced layers of insulation. So because we take that double layered approach, the simple answer is to double the voltage that we perform it at. If we're testing a class 1 at single layers of insulation at 1,500 volts, and it has to potentially break through 2 layers of insulation to show breakdown, then it makes sense that we double the test voltage. So again, if we took our previous example, we had a test voltage of 1,480 volts. We multiplied that by 2, we get 2,960 volts. Or, as close as it is in most standards, we would do the test at 3,000 volts. Okay, test times. Always refer to the standard again for any specified test times. But as a generalization, always make sure that the test time is the full voltage time that you're going to run the test for. We'll talk about ramping of voltages a little bit later, but any ramping or discharging of the voltage should always be in addition to the full test time. Now, as a general kind of rule of thumb, if we're testing in a testing type environment, the R&D world, the test is typically performed for a minute, 60 seconds plus, up to roughly 2 minutes, dependent on the standard that you're going to be performing it. For production or maintenance testing, that test is generally much shorter. It's normally performed between kind of 1 to 5 seconds. So it's a much quicker test because of the kind of strains of production line testing, the high volume of products coming through. There's no need typically for a 60-second per built product test. But always refer to your standard if you're in any doubt as to what time you should be performing the test. And finally, in terms of our test parameters, let's talk about the test limits themselves. So we're going to talk about setting our pass limits. So a pass limit is generally deemed good, providing that the current measured by the test equipment doesn't exceed our set limit, or as we referred to it earlier, our trip limit. Now, certain standards will suggest a limit for the current. You'll find in many standards that 5 milliamps is fairly typical, particularly in kind of lighting or household type equipment. It's generally specified at around 5 milliamps. Other standards will make a statement, like you can see on screen, that no breakdown or flashover shall occur. Now, what does that mean in the real world? Well, that would be indicated by a sudden and sharp increase in current flow from what it could be at stable. All of a sudden, we get a massive spike of current flow. Now, in the real world, in terms of testing, that's difficult to monitor for because we've got to watch the numbers. That number could increase sharply, and that also could potentially put our operators in danger because all of a sudden we've got this massive current flow flowing through the product. So we always try to use a test limit, a limit that's low enough to catch a failure condition, but not too high that it puts the operator at risk of a worse shock than possible. So always use a maximum limit when you're performing the test. Even if your tester is capable of measuring much higher currents, we'd always look to employ a test limit that's a sensible balance between safety and kind of problematic false failures, if you like. So again, if the standard refers to no breakdown or flashover shall exist, then what we need to do is we need to think about how we apply a test limit to our products. And a good method of doing that is what you'll see on screen. So firstly, take a number of known good products and perform the test at the specified voltage for a number of times on each product and keep records of all of those measured values that you take. Once you've got a significant number, 10 or more, from that, you can start to work out an average current flow. Well, take our measured values, work out the average of those values. Once you have that average, we then recommend adding a factor of 25, 30% on top of that measured average and use that as your pass limit. So as a good example, we've taken a number of products, we've measured them, and our average measured value has come out at 3.3 milliamps. What we do is we take 3.3, times it by 0.25, and add that back onto our original 3.3. So in this case, we'd have a limit of 4.125 milliamps. And we would use that as our threshold between pass or fail. Now, we often get asked, because most modern testers also have a lower limit, so we can apply a low limit to the equipment under test. And what is the function of that low limit? What does it do? It's true that for the sake of the standard, we just need to be lower than our trip limit. We need to make sure the product's safe. But there are situations where a low limit can help to determine whether or not we're actually testing the product properly. Now consider, if you like, we have our positive and we have our negative terminal on the Hipot tester. We plug the positive onto the product and we forget to connect the negative. Now, what we've done is we've effectively created an open circuit condition. And that open circuit condition will pass if we don't have a lower limit, because no current will flow back into the product. But when we've taken our measurements, we know that we've got a amount of leakage flowing. So the aim of the low limit is we can set a limit that's beneath the pass limit, but certainly higher than 0 milliamps. And that then allows us to have a kind of situation where we have a band of current flow. And if the current flow is less than that, then something's going on, potentially a poor connection, maybe the clip isn't on, we may not have put the main switch onto the product, so we're actually testing it into an open circuit because the live is not connected. So the lower limit is purely there as a quality measure. We can really kind of tighten up our tolerances on our max and minimum limits. If we know we're always expecting around 3.3 milliamps, we can use the lower limit as a catch-all situation for when things aren't properly connected. So we're just going to stop for a brief moment and hand the floor over to you guys. So we're just going to ask you, do you use the low limit feature within your test equipment? We'll give you a minute or so to answer the question, and then we'll come back. Okay, well, thank you for your participation in the poll there. Hopefully we may have convinced some of you to use the low limit feature in future. We will have a further poll a little bit later on in the presentation. So let's move on and start to look at the differences between AC and DC testing. Both of the tests can be used, providing that your equipment has the capability to do so. But the decision to really choose which one to use depends on a couple of factors, a couple of practicalities. So we'll talk through some of those that hopefully will aid you in making the decision that's best for the type of products that you're going to be testing. Now, most standards, when you read through the standard, will define the test voltage of those of an AC test. So generally the test voltages you see, unless there's a separate table for DC voltage tests, will normally be prescribed as those you would perform on an AC product. If you do need to do the voltage a DC test, there's usually a note somewhere within the area around the test voltages, and it's usually something along the lines of that you see in italics. Instead of being subjected to an AC voltage, the insulation may be subjected to a DC voltage of 1.414 times the value shown in the table. We'll cover why that's important shortly. But generally, there's no clear definition when you would use either method of testing. It is, however, typical, maybe not exclusive, to perform AC testing on AC powered equipment and DC tests on any DC powered equipment. So we're keeping the method of voltage application the same as that at which it would normally be powered from. But it's not exclusive to that, and we'll cover some of the reasons why shortly. So firstly, let's talk about the magnitude of test voltages. As I said to you before, most standards will allow testing to be either AC or DC. Most of them will prescribe the AC voltage with a note around the application of a DC test voltage. So as you can see in our table, if we applied 1,000 volt RMS test voltage to a product under test, actually we would end up with peaks of 1,414 volts. Now that peak voltage is exactly the voltage at which we would want to perform the DC test, so that we're effectively making sure that the product stress is exactly that as it would be at the peak voltage of an AC waveform. So when we choose to do a DC test, again, as according to the standard, we would normally multiply the voltage by 1.414. In certain standards, that may be approximated to 1.5. So as a good example, if we take our 1500 test voltage that we spoke about earlier for an AC test, we would simply multiply that voltage for 1.414, which will give us a test voltage of 2,121 volts, or approximately 2.1 kV. Now, the next thing we need to consider, and is a big consideration in the method of testing, is any capacitance in the test circuit. Firstly, let's have a think about what a capacitor is. It's very simply two conductors that are separated by an insulator. In many ways, when we perform the test, we can look at the actual test circuit as being a capacitor. We have two test leads, our positive and our negative, so they would be the two conductors, and they're separated by an insulator, which is hopefully the insulation within the product. So in many ways, we're always testing capacitance. However, this level of capacitance will change from product to product. Now, that could be in the case of fitted capacitance, i.e. potentially Y caps that are there to filter. But it could also simply be by lots and lots of the cabling within the product, whether that's the mains plug to the power supply or any cabling internally. As soon as we apply that test voltage, we're effectively creating a voltage difference between the conductors. And what happens in a capacitor is, as we apply an AC waveform, we effectively start to create what we call a reactive current flow. Current will flow across the dielectric because of the difference in the voltage. You can see that in the first waveform shape. As the voltage is increasing, we are effectively charging the capacitor up, so current will flow across. When we hit the peak voltage, then effectively we're discharging the capacitor, and so on and so forth. So we're constantly charging and discharging, which means there's a constant current flow across the levels of capacitance. Now, what that means is there's current flow, and that current flow is effectively being measured by the Hipot tester. It's what we call a reactive current. So this isn't true leakage current. This isn't a breakdown in the insulation that's causing current to flow from one point to another. This is just a natural phenomenon of capacitance. So why is that an issue? Well, effectively, when we're performing the test at AC, we're now measuring a combination of what is true leakage, but also what is reactive current flow. So we've got two current flows that are effectively being measured at the same time. So we don't know which is which. And what does that also mean is effectively the reactive current could be much greater than the true leakage current, which means we may have to adjust our pass limits accordingly, which could mean applying higher pass limits than normal, which could be potentially unsafe for the operators. Now, if we flip that and look at a DC test, well, there's only really one time where we effectively have a voltage difference between the conductors, and that is when we're initially charging up or ramping up the test voltage. So we apply the voltage steadily. There's obviously a voltage difference until we reach such a time that the capacitor itself is charged. And once that capacitor is charged and we've reached our maximum voltage, the voltage is stable. The current has dropped to zero, as you can see in the lower diagram on screen. So therefore, there's no reactive current flowing anymore. So when we perform a DC test, we tend to get a better measure of the true leakage of the product rather than this kind of reactive plus true leakage. Now, that also means there's a benefit on the production line because we can tend to set much lower and potentially safer test limits during the test. So whilst we're talking about capacitance and charging, we also need to talk about the ramp time and discharge times. So in a DC test, we have to predominantly ramp the test voltage, and that's in order to charge up the circuit and store and effectively reduce that reactive current flow. So once we've reduced that current flow, we're only now measuring the true leakage, but it takes time to ramp the voltage up. So we're effectively adding time onto the production. We're also having to discharge at the end of the test. Because now we've stored energy within this product, within this capacitor, there is a potential that when the operator comes to remove that product discharges that energy through the operator, and again, they receive a sudden shock from that discharge of energy. So it's important that at the end of a test, we make sure that the product is discharged. So effectively, we're adding time from the test time, both at the start in terms of ramping and at the end in terms of discharging or ramping down the voltage. So we can significantly increase the production test time if we do a DC Hipot test. So where we don't have much capacitance to worry about and we can get away with performing AC, it's much better for kind of fast moving production lines, if that's the right test to perform. Now, just a little note, most modern testers and certainly the Seaward products all have a discharge function at the end of a test to make sure the operator is safe at the point they touch the product. So once the test finishes, a discharge resistor is pulled automatically into the circuit, and that discharges any stored energy, keeping the operator nice and safe when they come to pick the product up. If we then look at the AC side of testing, well, from a ramping point of view, the test voltage is constantly increasing and decreasing. So we're constantly adding a ramp into the test voltage, a natural ramp via the waveform. So typically we don't need to worry about ramping the test voltage. And again, because the voltage is constantly changing, therefore the current across the capacitance is constantly changing. There tends to be no charge stored within the product. So there's generally less of a requirement to discharge after test. Again, those testers that have the function will automatically pull that discharge resistor in and do that, whether it's an AC or a DC test, but typically we don't need to worry about that. So an AC test is generally much quicker, whereas a DC test, we have to consider things such as ramp and discharge times. Now, there are certain standards that will require, even on an AC test, that we ramp the voltage. So if the standard calls for it, we should ensure that we follow the standard. Next thing to look at is polarity. So again, we're looking at the AC waveform. The cycle moves from positive to negative. So effectively, when we perform an AC Hipot test, we're stressing the product in both polarities, both from positive to negative and also from negative to positive as part of that test cycle. With DC testing, we only tend to perform the test in one direction. So we're only really stressing it from positive to negative. If we needed to perform a negative to positive test, well, that could be overcome by simply swapping the test lead connections and performing the test again. But as we said, with ramping and discharging, we're now adding additional time onto that initial test time. So there could be some time constraints involved with DC testing. So just to briefly summarize that conversation, AC testing, from an advantage point of view, overall test times are usually much shorter because we haven't got to consider ramping and discharging. And it's also not necessary to do the discharging. And the insulation is stressed in both polarities. From a disadvantage point of view, we are measuring total leakage current, both breakdown current and any reactive current flow due to capacitance. And as a side note to that, that may mean we have to apply higher pass limits, allowing more current to flow as part of the test circuit. Therefore, that could become less safe for the operator. From a DC point of view, well, the advantage is we get a better representation of the true leakage of the device under test. We don't see this reactive element so much in a DC test. And that means that pass limits can generally be set at much lower values. If we know the current isn't so high, we can set a much lower value for the breakdown, which is much safer for the operator. A DC test is always going to be better for any kind of capacitive circuits, and we certainly recommend, if you have a capacitive circuit or highly capacitive circuit, a DC test is definitely the better one. However, from a disadvantage point of view, on a high-moving, fast-moving production line, overall test times are going to be slower. So that may need to be considered in terms of the throughput on the production line. You must ensure that the device under test is discharged, so we don't get a sudden and sharp discharge through an operator that's handling a charged product. And the DC test only stresses the insulation in one polarity. So as you can see, there are pros and cons to using either method. Ultimately, it comes down to capabilities of the test equipment and the type of product that you're testing to determine which is best for you. Our general recommendation would be, if you've got an AC product, then you perform it on AC and the test is good and within limits, great. If you are seeing failures on the production line, potentially it may be worth trying the test at DC If you're still getting failures, then that would indicate there's something potentially wrong in the product. However, if the current flow drops down to safe amounts, it's probably due to the capacitance within the circuit. So we're briefly going to move on now and just have a look at some of the test standards, probably the more common standards that we see through our customer base. So we've put 4 main applications up there: lighting, household equipment, measurement, control equipment, the standard that us at Seaward making Hipot testers have to comply with, and then kind of audio, visual and IT equipment. And we've broken this down so you can see the differences between the kind of voltages. They range from anywhere from kind of 400 volts at the maximum up to kind of 11,000 volts, depending on the type of product that we're testing. You can see the limits. Certain standards will apply a value that you can follow. It is more common to see this no breakdown as a specified kind of trips level. So in that case, refer back to earlier on in the presentation, use the method of profiling good products and come up with a limit that makes sense for your production line. You will see that certain products will specify a ramp. So 61010, for example, for laboratory use, you can see that we should ramp the voltage from 0 to its prescribed voltage within 5 seconds. And you can see test times are fairly similar, somewhere in the region of 1 to 4 seconds. As a kind of example, household equipment, if you're testing a product, a 240 volt product, it's typical that a class 1 product will be tested at 1,000 volts, whereas a class 2 or double insulated product would be tested up at the 2,500 mark. So within the standards, the tables are a little bit more prescriptive than maybe the table you see on screen, and they will define the voltage generally by the type of product, the operating voltage, and the kind of method of safety. So whether it's a class 1 or a class 2 product, most standards will give guidance as to the correct voltage to perform in those different kind of circumstances. So we're just going to finish this up now with a quick poll, and then we're going to have a couple of video demonstrations to show you, showing some breakdown, showing a flashover condition, and also the difference between the readings that you may get on an AC and a DC test on exactly the same product. And that will show the kind of total leakage measurement, including the reactive element, versus kind of a true leakage measurement. So before we move on to the videos and we close the presentation, we're just going to ask you one more question. And that question is, which method of testing do you employ on your production lines? Is that AC testing, DC testing, or do you do a combination of both? We'll give you a minute to answer the questions, and then Brad will come back and give you an update as to what we all voted, and then we'll show you the videos.